Hey, this is Steven, and today we're going to teach you how to not blow shit up. I'm an electrical engineer, and today we're going to talk about reverse polarity protection. Now, this is used if either on the production floor or the customer can potentially reverse power in your circuit. This is a safety feature, so it's very important that you pay attention. So we're going to go through this today. But I've done it with a little bit of a twist. I have asked the almighty ChatGPT about the methods of doing reverse polarity protection. So I thought it might be fun. Hey, let's go through what it thinks, and then let's see how good the AI actually is. So let us begin. And if you pay attention, your circuits will be safer than ever. So the first one is series diode. A diode is placed in series with the power input. I don't usually use that language. I don't tell my coworkers, place it in series with the power input. So all that is, we're going to go through a diagram right here. Here's my connector. I left a lot of space for 12 volts so I can put components, and then here's our ground. So what we're just going to do is, when I mean in series with the power input, this is all they mean. No big deal. So pros: cheap, simple, and easy to implement. Simple, absolutely. Easy to implement, oh yes. Cheap, well, if you have a lot of power, then you need a diode that can handle it. So probably. Cons: voltage drop. 0.7 for silicon diodes, 0.3 for Schottky diodes. Huh? In school, yeah. In real life, no, you can't rely on these numbers. That voltage drop depends on both temperature and current. So this may not be right. I've seen Schottky diodes that have a voltage drop of closer to 0.6 once you load them down. So you need to look at this on the data sheet. You just cannot use these numbers as gospel like they did in school. But this does reduce efficiency, which is a big deal if your product operates via a battery. So power, in this case, power equals voltage times current. Your voltage is whatever it is in the data sheet. So it's a little bit harder to tell exactly how much it'll use. I'm sure you can guess your current. Temperature, So you'll just have to make an educated guess. Item 2 here, same theme, but with the Schottky diode. So this one's easy. So what we can do is just take that out, add Schottky diode right there. For your very green entry-level people, difference is this has the squigglies right here, and it's constructed a little bit differently, but we don't have to worry about that part. You can get them, and they're easily available. No big deal. Pros: more efficient than silicon diodes. Yes. Still wastes power and produces heat. True. Now let us move on to the third one. P-channel MOSFET. Whoa. A P-channel MOSFET is placed in the positive rail with its source facing the power input. It blocks reverse voltage by remaining off when polarity is incorrect. True. But keep in mind, and this includes diodes, there's always going to be some reverse leakage. In this application, reverse polarity, we don't care. But it's something to keep in mind when you use diodes and MOSFETs elsewhere. Now, pros: very low voltage drop, only a few millivolts. Depends on your current. So I'm saying bullshit. Maybe. High efficiency. True. Requires proper gate drive. Pull down resistor? Huh? I mean, yeah, but here's how to do this. I'm not quite happy with how that explained it. So we're going to find give me a PMOS right there. So we're gonna reverse that. That is correct. Let's move this a little bit right there. We'll put actually, no, we need resistors. So let's do a resistor. Let's go with the US symbol because I'm in the US. So we need one right there. Then we're gonna copy and paste. And we need one right there. Then we're gonna wire it up. Then we need to put a ground in here. Because I'm starting out with 12 volts, I'm going to make these both 100K. That's a good value to use. This is how we can do it. Okay. So notice how the body diode, anode is on the left, cathode is on the right. So what happens is this conducts through the body diode. Then we have our, in this case, 6 volts going on here, which turns on the gate, which then really turns the whole thing on. But it happens super quick, so you're good. So this is how to do this. You may, instead of having a resistor right here, you may have a Zener diode. You would want that if your voltage is really high, because there's a spec for how high VGS can be. In this case, it's VSG, because it's a P channel. So that's how to do this. Let's go back and see what else it said. Requires pull-down resistor. Yes, I didn't mention the Zener though, which you may need. And P-channel MOSFETs have a higher RDS on than their in-channel counterparts. For the same package size, that's true, but P-channel transistors have come a very, very, very long way. Like, it's no big deal to find a RDS, that's the resistance between your drain and source, to be 20 milliohms. So speaking of that, I want to come back here though, because this Pro is very low voltage drop. So if we go back, and okay, if this is 20 milliohms, but what's my current here? It's because you can get these that can do 100 amps. So if I'm at 10 amps, yeah, I'm probably at 0.2 volts if I spec this to be beefy, but you don't have to. So the millivolts can be off depending on your application and how much current you're going to go on there. As a side note, if you were to put a capacitor in parallel with this R1 right here, you get soft start functionality. That's kind of beyond the scope of what we're talking about, and you got to look at the data sheet and the safe operating area. But it can be done for the price of one little teeny tiny little capacitor. This is one of my favorite methods to do for reverse polarity protection, just because it is that efficient, and a lot of the stuff I do is battery powered. Now, let's go next one, in-channel MOSFET with a charge pump. So what they're basically doing is they need that 0.7 volt voltage drop for VGS. So they're making the gate higher than the drain. I can never remember which one is which. I always got to have a diagram. Or source. Still source. Yeah, source. So even I get it wrong sometimes. But anyway, yeah, charge pump, yeah, it'll work, but then you got to find a freaking charge pump. I don't do this because P-channel's that good. Now, Next one, series fuse and parallel diode. Let's just do that right off the bat without even reading this. This one, I have kind of done it. The one next is the same thing, but with a PTC. So we'll just lump this all in one. So what they're talking about here, let's get rid of this. So we're talking a diode. And we'll do we just do a regular fuse. Here's your poly fuse here. So we'll get rid of, you know what, we'll get that right there. Then we'll get you right there and you right there. All right. So we have a reverse polarity condition. So your plus 12 volts will be down here and go through here and then go through here. Now, if it's a regular fuse, it should be should be a fast acting fuse. And then once the current exceeds whatever the fuse range is, it pops. I am not the biggest fan of this solution because fuses are big, so you would need a lot of board space. In order to replace the fuse, your customer is going to have to open the unit that was sold to them. I don't really want them doing that. Alternatively, you got to modify your case and get this fuse user accessible. So that adds cost. Plus, you got to wire it up. Sometimes, depending on the product, it is a good idea. Just you got to be aware of how you're going to implement a fuse before you do it. Now, a polyfuse, that's the PTC thermistor, resistor, positive temperature coefficient. So as temperature rises, resistance rises. Temperature rises enough, resistance is so high that this effectively opens the circuit. So I've done this and it's not my favorite. Polyfuses take a while. And the current has to be a lot higher than whatever it's rated for. But all that's in the data sheet. So you can always look that up. But also, in the meantime, whatever current is going through here, this component's got to take. So it's probably got to be pretty oversized. So I don't see too many downsides. Sorry. I don't see too many upsides here of doing this. One of the reasons I had to do this in a product is because, for compliance reasons, because we called this safety critical. And I didn't want to have to redo how we did circuit protection in order to recertify. I didn't want to have to deal with that nightmare. So, but it works. It certainly is a valid method. Now let's go back to the AI. Pros for the fuse, effective, cool. Cons, fuse must be replaced. True. Polyfuse or PTC, it heats up and disconnects power. Self-resetting, okay, this is true. After a while, it is going to cool down and you can use your device as it was intended, assuming you reversed the reversed polarity, so you have correct polarity now. But that can take a while. Your customers aren't going to be used to that, and it's going to throw them off. But it does work. Another thing is that depending on how you do it, depending on your current, if it's on the higher end of current, these devices can be rather large compared to other parts of your circuit. They can be tall, which can cause issues with how the bloody thing's going to fit in the circuit. Not as efficient as MOSFET-based solutions. I'm not quite sure about that one. because your MOSFET, it's going through the MOSFET all the time. Meanwhile, this, if your current's low, your resistance is low. So not too much of a loss there. I could see where this is coming from, but it ain't that bad. Here's another one. I haven't done this, but I designed it. So a relay is configured to only activate when the correct polarity is applied, using a diode in the coil circuit to prevent activation in reverse polarity. All right, let's do this one. So I thought this is actually rather interesting. So let us do relay. Let's see if we can get a, let's see, single pole, single throw. There we go. I'm going to do it like this. Get rid of this stuff right here. All right, so what we do, hey, don't do that. Okay, so we put our voltage here, and we put it here. Remember, we need a, let's just use a Schottky diode. Always got to have your flyback diode. We put that in there. Flyback diodes keep crazy amounts of voltage when this coil turns off. So we do that. Then we do, oh, by the way, we have to do a, I'll get it. Do that right there. We have ground. Right there. Then I need to copy you. I need to paste you. I need to put you up and get rid of you. You know what? You're in the way. You need to move. Keep you down there. We'll do that right there. All right. So let's explain this. So normal operation, our 12 volt goes in here. We go through the Schottky diode. We go through the relay coil right here, and it energizes the circuit. Hence, our 12 volt flows to the rest of our circuit. Reverse polarity, 12 volt goes here, goes through our coil, I guess through our Schottky diode also. But it doesn't matter because it's blocked right here. Now, this does have some advantages. That's pros. No voltage drop during operation. Minimal voltage drop. It's fine. But yeah, I think that's close enough. Close enough. Using a diode in the coil circuit to prevent activation of reverse polarity. That's why I had to use the second diode. Mechanical relays are slower and less reliable over time. True. Turn on and turn off 15-20 milliseconds. Our MOSFETs would be measured in nanoseconds. Less reliable over time. True. Because we have contacts here and there. And then at the initial turn on, it's probably peak current because of capacitive load. Basically all the capacitors in the circuit. So it creates a brief period where your current is very high. So that wears out the contacts after a while. What this the AI did not mention is that so my company, we sell a portable product where it is used outdoors, which means, and it's big enough where you need like a cart. and you're kind of in remote locations, so you're going through the grass and whatnot. If the terrain is bumpy, that's just not ideal for a mechanical device such as a relay. So you can get relays that can handle more G-forces, but it just won't be as good as, say, the diodes or the MOSFET. So it's something to keep in mind is what environment is your product going to be used in, and is it going to be bouncing around all over the place? But overall, this is simple, effective. I have no problem with this method, and it can be high current. So another one I have looked at, but I haven't implemented personally, it's called an ideal diode. Specialized IC controls a MOSFET, usually in channel, to act like an ideal diode with no voltage drop. So your normal diode has the voltage drop as we discussed. This one, nowhere near as bad. Pros, extremely efficient, very low voltage drop. We like that. More expensive and requires an IC. So this one suggests the LM5050. I happen to have the data sheet of the LM5050. So they call it an O-ring FET controller. Basically, another way to use one of these things is for if you have more than one power source. But not today. So this one in particular has an external MOSFET. So you need that for higher current. For low current applications, they have it built in. If you look, fast 50 nanosecond response to current reversal. Awesome. Oh, and we use it to replace diode rectifiers. Don't get hung up on the word rectifier. Diode. And power distribution networks, thus reducing power loss. And these can have a high range, but you got to spec your MOSFET correctly. So 2 amp peak gate drive current, excellent. So these things are good. There was one problem though. I had an application where I did actually need this capability right here. And this was during all the supply chain issues a few years ago. So supply chain issues, man, I couldn't get it except for one, and there was a ton in stock. So I made my design, and it looked good. I was happy. And then I checked supply a week later, and all of it, and I mean all of it, was wiped out. I was pissed. All that work for nothing. So I had to do a different design. So that's why I tend to not go for specialized ICs sometimes. Sometimes the basics just work. So I would encourage you to look at this into more detail. Just, it can be the bee's knees. Now, last one, and they should have put it first. Using polarized connectors or keyed plugs prevents incorrect insertion. Pros, 100% effective when implemented properly. True and true. I mean, if you can't physically connect it backwards, then you don't need any reverse polarity circuitry. Cons, does not protect against intentional misuse. Well, we don't care about that because it's intentional. And hopefully your product manual says how to connect the bloody thing properly. And you know what? You just don't have to honor the warranty. Like, it's not a bit intentional misuse. You don't have to worry about that in practice. What you do have to worry about in practice, though, is incorrect wiring. So that takes two forms, which is In my case, for a product, we let the customer use their own lead acid battery. And then we sell the terminals that can plug into this connector and the battery. Just two little terminals. So you better believe we need reverse polarity, because customers can and do hook it up backwards. That's not the only thing you need to worry about. Now, let's say this is internal to the product. So how's this cable assembly made? If it is made internally, meaning you have people in your company putting in the pins and then the wires and soldering and all this, or crimping and all this other stuff, they're making it in your place, you need reverse polarity protection. I have been the guy on the production floor that does this. After a while, it does crazy things with your brain. They will get it reversed. It doesn't matter how good your work instructions are. It doesn't matter how clear your bloody pictures are that show them how to do it. It will be messed up. Now what if you outsource production of your cable assemblies? Well, they will do a lot better, but they will still mess it up. Now, depending on how bad a reverse polarity situation is, which you should test all the possible faults in your product. But I can tell you, sometimes it doesn't happen. I've seen it. And a lot of times I just can't believe it, but I have seen it. So if a vendor messes it up, though, then you've got some recourse, because then you can say, hey, you didn't make it to print, and you caused us some damage before we figure it out. Usually companies eat the cost, but you got some recourse there, and you can teach your vendors. Sometimes you got to teach the vendor, make my shit right. Otherwise, we will be on you. So ideally, this should be, out of this whole list, this should be number one. If you can do this, you can be home free and not have to worry about circuitry. But when you do, so I like mechanical keying, ideally. Diodes for low current, everything else P-channel. That's how I do things in the real world. These other ones, some of them I have done or thought about, but they're not as good. So comparison table right here. We kind of talk about these in detail. Best choice, absolute protection, fuse plus diode. I guess a fuse, but nah, I like these diodes and MOSFETs. Keyed connectors, yes. So I asked it a second question because I noticed that it said, here's the common methods. I'm like, well, what's the uncommon methods? So one of them was a little bit interesting. It was using a bridge rectifier. So a full wave bridge rectifier, 4 diodes in a diamond shape. I thought this was kind of interesting to do. So we can show that real quick. So all I care about is the symbol. So we're going to do that. We're going to wire that. Wire that there. Wire that there. Hey, don't you do that. Then what we'll do, this is our ground, just wire that right there. So we're gonna simulate the rest of this circuit. With that resistor. So then we'll move this down here. Correct polarity. go through here, go through this diode, go through the rest of the circuit, go back to the negative terminal, and then it goes to ground. Polarity reversed. So we go back through here, this diode, right up here, back down, over, back through here, and then out. All right, so now we got a circuit that works in both directions. Awesome. Except I really don't want to teach the customer they can plug things in the wrong way. Also, now we've got 2 diode drops, plus all the power inefficiency from there. So really not ideal for battery applications. But by golly, man, if you need something that works no matter what, I guess. I have never implemented this personally. So another thing I want to mention, since we're here about keyed connectors. So sometimes you're not in control of the connector itself. Sometimes you are in control of the pinout. So I put 3 here because if you just did the 2, power and ground, and you reverse it, well, there's your reverse polarity. But say 3 here, I reverse this, well, there's nothing here. So the circuit won't work. So depending on how you do your pinout, you could protect against reverse polarity. So something to think about. So that was cool. Another one, Zener diode plus resistor. Yeah, okay. Rarely used for primary protection. Yeah, because I want primary protection. This one, SCR-based reverse protection, we're not going to go through that. Never seen it done. Comparator plus a relay. Needs additional power to operate. That means a second voltage source. Nope. We're going to skip that. Optocoupler. Thought that was interesting, but it requires additional power source. Nope. Gas discharge tube plus MOV protection. Nope, because we're not. I'm doing like 12 volts, man. Like for most people, like high voltage power distribution. Nope. That's major voltage right there. So nope, I'm not. Super cap. I thought this was interesting, but immediately your cost is high. And then your voltage has to be really low. So, nah. So then electromechanical lockout. Some designs include mechanical switches or locking connectors that physically prevent incorrect polarity from being applied. Cool. I like that. Custom hardware. No. Custom hardware means cha-ching. Don't want that. Aerospace, military applications where 100% reliability is required. Okay. Well, I suppose they can afford the cha-ching. Most of these final thoughts. Most of these methods are inefficient, costly, over-engineered compared to MOSFETs, diodes, and fuses, which are the go-to solutions. True. So I think we went through a whole bunch of different methods here. So with this knowledge, you can now protect your circuits from boom, or pop, or fizzle, or just your product not working. You can prevent customers from having to return it. Warranty. This solves problems. And it is safety, which should be, hopefully, in your company, one of, if not, the most important topics. So I'm going to sign off here. Please let me know what you think, or if there's anything else you want me to go through. Thank you.